Let's get started, people. Good afternoon. My name is Rodrigo. We are live on the LuxOUG Virtual Tech Days. We will have a full agenda with great names for Oracle community. So first of all, thank you for attending the event. Our group was founded in 2019. We already delivered 7 webinars. We have a total of 124 members on our portal. We have a lot of content about several topics like cloud, engineering systems, and a lot of good stuff. So if you are not subscribed on the LuxOUG, please do it. It's a completely free membership. If I haven't said enough, thank you, board member of LuxOUG, because we made it happen. We made the event go live today, and we will have a lot of fun this week. So I will give now the control to Toon Kopperlaars. Will be our first speaker today, and this is us, LuxOUG members, the board member, André Ontalba, Carlos Magno, Fernando Simon, Leonardo Lopes, and me. So now, Toon, the control. I will stop my screen now, and you can share yours.
Okay.
Okay. So I will stop share.
Okay, let's start.
Yes.
Good afternoon, everybody, and welcome to this talk, which has the title Database Performance Core Principles. My name is Toon Kopperlaars. I work within the Real World Performance Group inside Oracle. Here's a little bit of myself for those of you who do not know me yet. I've been using Oracle for quite a long time, and my special areas of interest always has been application development, and especially database design and using SQL and PL/SQL to its fullest. I'm therefore also a big fan of using the database as a processing engine, and I'll have some more to say about that at the end of this talk, and not just as a layer to persist data. Over a decade ago, I wrote a book, which you see on the right there, Applied Mathematics for Database Professionals. If you want to have some more information about what that book is about and whether it might be interesting for you, just drop me a message and I'll give you some more details on that book. But let's start with today's talk. Now, I always have a little bit of a dilemma when I do this talk. This is a talk that I've been giving in various forms and versions. So this is the latest version of this talk. And the dilemma is, I'm going to talk to you about database core performance principles. But it's probably not going to help you much immediately, because your applications will very likely need to be changed to comply with these performance principles. And obviously, in the real world, that often cannot be done, right? Because they need very likely re-architecting. So the dilemma here is that I will talk about it, but only to create awareness of this. And my hope then is that you can use the knowledge of this talk to influence future application development endeavors within your organization, and maybe push them or nudge them a little bit towards a slightly different architecture that makes much better use of the computing resources that these applications use. Now, performance core principles, why do I want to talk about it? Because if you're in charge of your, or in any way involved in the performance of applications, you should be comfortable with questions that I have up here. If you have a single CPU, how many processes can be active at any one time? One, right? If you have 4 CPUs, can only be 4 processes active on 4 CPUs on 4 cores. What's the implication when there are more processes that want to run than there are CPUs? I'll talk about that. And what if my process needs to access an external resource, typically the network or an I/O? What happens to your process in the operating system? And what happens once that external resource request has finished? How does my process continue get back on CPU? And what's the difference between user and sys CPU? These are the kinds of questions that I think you should feel comfortable with, because they underpin the core performance principles that I will be talking about. So here's the overview of my talk. I will start with the fact that Oracle is a process-based architecture and the implications of such an architecture. That's the first bit of this talk. Then I'll touch upon these 3 concepts called response time, throughput, and database time. So then I've laid down all the knowledge, the principles that I think you should be aware of. And then I'll show, but along the way, I probably will have mentioned it also 1 or 2 times. I'll show that application development nowadays has fundamentally moved away from these core principles, which is why we see so many applications out there that either run or scale very badly or require a huge amount of computing resources to run satisfactorily. So let's start with the implications of Oracle being a process-based architecture. So what do I mean by a process-based architecture? Well, if you connect to the database, a process is forked, is started, whose sole purpose it is to service the database calls that you then can send to the database. Yeah? And typically in a modern application, you are not connecting anymore to the database. A connection pool will have done that. But the principles are the same. So the connection pool will have pre-spawned all these foreground processes on the database server who are there to receive database calls and then service those database calls. Now, for a process-based architecture, which Oracle is, to perform efficiently, a few things need to be in place. The operating system needs to be able to get the process on CPU as quickly as possible, because only when a process is on CPU can it do useful work for you. But then there's a second thing. Once a process is on the CPU, preferably you want to have that process stay on the CPU as long as possible for the duration of the database call. And that has 2 dimensions to it. One, the process should not go to sleep voluntarily a lot, and I'll explain what I mean by that. And the process should experience as few involuntary sleeps as possible. And I'll explain that also in the next few slides. So let's start with the first one. Here I have my foreground process, and it's currently idle. It's sleeping. It's not working on a database call. And here's my CPU. So now the application issues a database call. So what happens? The operating system basically receives an interrupt via the network interface card. Yeah? It sees a package arriving on a certain socket number. It then needs to figure out what's the process listening on this socket number. It finds that process and then asks the operating system scheduler to schedule to get that process on the CPU. Yeah? And once it's on the CPU, we, or the Oracle foreground process, can start working on the database call. Now, all work performed by the OS and the scheduler before the process is actually on the CPU is a little bit of sys-CPU going on. It's operating system code being executed before the process actually hits the processor and can start doing useful work. Now, in order to get on CPU as fast as possible, there's this thing called current CPU utilization playing a role. Because on a CPU, there can only be one process active. A process is either on the CPU or it's off the CPU. You can't be 50% on the CPU. So at any point in time, when my process receives the interrupt and wants to do work, it needs to go to the CPU. And let's say if your CPU utilization is 50%, current CPU utilization, then you have a 1 in 2 chance that the CPU is currently working for another process, is currently occupied by another process. Yeah, so then you have to wait a little bit in the runtime queue of the operating system before you can get your go on the process. Yeah, and this chance increases dramatically with the CPU utilization. Yeah? So if you have a CPU utilization of 80%, there's a chance of 1 in 5 that you actually get scheduled immediately, or 4 in 5 that you have to wait a little bit on the run queue. Now I'm showing this here just to bring over the concept, but I'm using a single core machine to explain this concept. It's of course less straightforward and a little bit more sophisticated with multiple cores. Now the CPU utilization, the current CPU utilization does not only influence how fast your process can get on CPU. It also has influence on the overall duration of the database call. So it has a measurable impact on the response time of the database call, which becomes noticeable once you are, let's say, 60–70% busy rate or higher. And I'll show you that in the next graph here. So what I have here, again, I'm explaining this concept using a single core database server, is the formula for the response time. The response time of a database call is the service time, the time that it's actually required to do computation on the core, divided by 1 minus the utilization, the current utilization of the core. So let's say if your current utilization, which I have here on the x-axis, is 0%, you're the only one on the server, you get scheduled immediately and you can have all your work done immediately by this core. So let's say your service time is 1 second. Your response time will also be S divided by 1 minus 0 utilization will also be 1 second. But if your current utilization is 80%, your response time will be S 1 second divided by 0.2, 1 minus 0.8. So divided by a fifth, multiplied by 5, your response time will be 5 seconds. Yeah, so and the difference between what you actually wall clock time your database call is taking inside the operating system versus what it actually what it only requires to be done to be doing on the CPU, the difference is queue time. You're queuing and waiting for your go on the CPU again. Now every system starts queuing at some point. This again more complex with multiple cores, but even in multiple core database servers, at some point you will see queuing going on in the sense that processes can't be on the CPU all the time that they want to be on the CPU. This all depends on the arrival rate of your calls, the service times, the number of cores, and the current CPU busy rate. Yeah, but a significant time of the response time of a database call can be queuing time. That's one of the reasons why you never want your database server to be running at full capacity all the time or way beyond 70% busy all the time. So that's about getting on the CPU as fast as possible. The second thing that I mentioned in the introduction is you want to stay on the CPU. Once the process is on the CPU, you want it to stay on the CPU for as long as possible. I have a little animation here to show that also. Let's suppose you want to insert 10 rows. And there's two approaches. You can issue a single array-based or stored procedure call, which does all the 10 inserts, yeah? Or you can have an array-based insert where you bind 10 records into an array and you use the bind interface to issue a single insert statement, which will then insert 10 rows. Or you can choose to call the database 10 times, each time a single row database insert. Yeah. So on the right, I'm going on the core, I'm inserting those 10 rows. So I'm on the core a little bit, and on the left, I go on and off the core, on and off the core, on and off the core, 10 times. 2 approaches of inserting 10 rows. So on the left, you have voluntarily chosen to sleep 10 times. That's what I mean, not go to sleep voluntarily a lot, because you've issued a call, you went on the CPU, you used a little bit of the CPU to process the 1 row insert, and then you chose to, and then your call was done. So you voluntarily, the process voluntarily goes to sleep again. And then it has to be scheduled again. Yeah, 10 voluntary sleeps, 10 schedules. On the right, you've only voluntarily went to sleep once after you've inserted the 10 rows in a single database call. Now, there's also another thing going on, which is often overlooked and thought to be of negligible impact on the performance. And that is, for a process to go on the CPU, it has to, on the chip, you have to execute what's called a thread context switch. And a thread context switch is basically restoring your process's state on the core. Yeah, so all the values of the registers, the level 1, the level 2 caches, etc., they have to be flushed of the process that was just on the core prior to you going on the core, and have to be reinstated with your process's context. Now let's have a look at a thread context switch. That's microcode execution inside the core on the chip. So I have here a visual that I found on the internet, which shows all kinds of things that a core can do with increasing number of clock ticks that it takes for such a thing to do on the core. And this is a logarithmic scale. Yeah? So it takes 1 clock tick to do a register add, or etc., to do a branch if or a floating point addition. Level 1 read, level 2 read, I'm getting into the 10 clock ticks now, level 2 read, etc., etc. C function direct call, maybe 50 clock ticks to do that, etc. Yeah, so it's these kinds of things where the Oracle kernel spends most of its time executing code in the SQL engine. It's all these kinds of instructions on the chip. Now, I don't know if you noticed this last one, but this last one is the thread context switch. That's the most expensive thing for a core to execute. Yeah. Over here it says 10,000 to 1,000,000 clock ticks. It depends on the core, but modern cores are probably more into the 10,000 clock ticks for a thread context switch to happen. And this has to happen. These 10,000 clock ticks are executing microcode that have to happen to get your process's context reinstantiated on the chip. Yeah, imagine in 10,000 clock ticks how much of these things you could have executed. Now on a 3 gigahertz core, this is 0.33 milliseconds, but we're not going to use that one. Let's use this one. On a 3 gigahertz core, this is still 3 microseconds, 10,000 clock ticks. 3 microseconds. Let's put that into perspective. A fetch by row ID inside the SQL execution engine takes, depending on how big the row is, etc., anywhere up to 10 microseconds. Yeah. So this is not negligible. I immediately get a knock-on of 30 to 50%. If I do a single row fetch or a single row insert, is maybe a little bit more depending on the number of indexes that need to be maintained. But it's just to show you that it's not a number that you cannot ignore, especially if you choose to call the database many times, which is what modern applications do nowadays. But there's another thing going on. Yeah, so I mentioned 10 schedules, 10 context switches, and earlier I mentioned the network interface interrupt on the socket number, operating system entries and exits. But once my process is on the core, I'm not immediately inside the Oracle SQL engine. I have to descend the Oracle kernel into a few layers, get the message, unpack the message, see what needs to be done, etc. So there's also 10 Oracle kernel entries and exits going on. And that too is not negligible. So like a thread context switch, it's measurable overhead. It's measurable if your calls are small and fast. If you're using a row by row approach, it's a thing that is actually measurable. We tested this using a lab environment. Let me give you just a summary of those results. So what we did is we created a simple batch process. We built it in Java, single-threaded, just keeping it simple, single-threaded batch Java process. In a tight loop, it would issue a mix of single row selects, single row inserts, and single row deletes. Yeah, all issued sequentially over JDBC to the database, generating 9,000 calls per second. So 9,000 calls per second and very easy, simple SQL statements, not taking a lot of time each in themselves. Then we used the Linux perf utility to profile the foreground process. And the perf is basically a utility which enables you to sample the foreground process. And what does it sample? It samples the current call stack that your process's execution is in. So we're sampling, let's say 100 times per second, the Oracle server process while it's working on these calls, 9,000 per second, to see where in the Oracle call stack we spend most of our time. And then using a flame graph, you can intuitively visualize that. So let's briefly talk about how to read a flame graph. So what I have here is a program that has a main entry point and then can call P1 or call P9. From P1, P2 can be called, from P2, P3 can be called, and P9 can also call P4. And we've sampled this program while it was running. And what we do is in the flame graph generation, you sort all the code stacks, and vertically you see the call stacks, and horizontally is a representation of how many times that call stack was sampled, which ends up in the top surface being where all the time is spent relatively to each other. Yeah, so here you'd see we're spending most of the time in P2, especially if we take P3 into account with P2 also. Yeah, we're spending a lot of time in P9, a little bit in P4, and a little bit in P1 over here. Now let's show you the flame graph of that little experiment that we did. I'm just going to show you the big ones in here. So all over here, that's SQL execution engine code. You see a delete, an insert, and other stuff going on, fetches. This is all SQL execution engine code that has been sampled. But roughly a third of the time, we're spending time into these big mountains here. Yeah? So what's that? That's receive and send. So this is code that receives the database call, yeah, where we actually have to read it from the socket in order to get it before we can look at it, interpret it, and start executing the SQL. And this is code sending results back. So with a fetch, we have to send a row back, or with an insert or an update, we have to send a return code back. Yeah, so this is writing into the socket back to the application server. That's a third of the time. A third of the time spent in user mode, just receiving and sending, getting in and out of the Oracle kernel. This is useful time. Yeah, so it's, again, this too is not negligible on a per call basis. Now, I can imagine you can't do flame graphs on your database server, but you can spot this phenomenon in an AWR report. You can spot and get an idea about the overhead of entering and exiting the Oracle kernel many times per second. So here I have a few snippets from an AWR where we're going to the database server almost 49,000 times a second. And the database server itself was fully CPU bound, working, so no major wait events. And if you look at time model statistics, you see this phenomenon where DB CPU is way higher than SQL execute elapsed time. Now, SQL execute elapsed time is CPU bound. Yeah? So this is all CPU. Why do we have a lot more DB CPU? Because over here it says 18,000 seconds spent executing SQL, but in total, 28,000 CPU spent by all the foreground processes. That's the missing accounting of the entering and exiting the Oracle kernel. So what we spend here is not attributed to the SQL execution, but it is attributed to the foreground process usage of CPU. Yeah. So here we see 10,000 seconds, the difference between these two figures, of CPU spent on entry and exit, which is what you see on database servers that are servicing an application that does that, and all the application does is row by row approach, calling the database many times per second. Yeah, so that's a lot of CPU seconds that you're spending on basically stuff that needs to be done but does not add any value to your application. Executing SQL adds value to your application. You can actually spot the SQLs that are hit by this overhead the most. Again, under the assumption that you're CPU bound. If you can see SQLs that have where this percent CPU and percent IO do not nearly sum up to 100%, the last one, for instance, you see that this one is roughly hit by this overhead, almost, how do you call it? By a factor 2. And here we see 22% overhead. Here we see 13 or 12% overhead and another 12 or 11% overhead. Due to these selects very likely being primary key lookup selects and a fetch by row ID, which execute really fast in the SQL execution engine. Now, this overhead is not just on the database server. Every process has this overhead. What I'm showing here very quickly is the flame graph of the JVM of our lab test. So in the JVM, we also see these two flames in order to send out 9,000 times a second a SQL statement over JDBC across the network. Yeah, so here we also have a send and receive flame, taking roughly a third of all the CPU cycles that your JVM is burning on your application server. Useless stuff going on. Now, if you want to see the full story, I did a YouTube video on this experiment a few years ago. I have the YouTube video here, or you just go to YouTube and search for Kopperlaars, my last name and database. I think it's the top one. And then you can see the full report of this lab. Anyway, the status so far is that process architectures have measurable, notable per call overheads. Yeah, and I've mentioned so far the OS interrupt, figuring out which process to start. The scheduler needs to do its work to get the process on the CPU. Microcode execution needs to execute on chip to get your process state reinstated. And you need to enter the Oracle code before the SQL engine actually can start doing useful work. So the last thing about these core principles is a process should experience as few involuntary sleeps as possible. I have an animation again here. So let's say I now have 3 processes, and each process wants to do an insert of 10 rows in a smart way, an array-based insert or a call stir procedure, which does the 10 rows insert. And they all receive the database call at the same time. So what's going to happen? They get scheduled round robin based or whatever strategy is used by the operating system, but each in turn, because there can only be one process on the CPU at a time. That means that a process will get on CPU, it starts working on its 10 rows inserting, but it will get interrupted and asked to involuntarily go back to sleep while it wasn't done yet for another process to be on the CPU and have some slice of the CPU. Yeah, so those are involuntary sleeps that processes can experience due to the fact that there are more processes that want to go on CPU. And you want to minimize those also, those involuntary sleeps, which basically means that in this particular situation, it would be far better to have one process insert 30 rows instead of having 3 processes at the same time compete for the one CPU and get those 30 rows inserted. Now, the number of processes per core that your architecture requires has an impact on the scalability of your architecture. Let's say I have an architecture where I roughly have one process per core. And with one process per core, with 4 processes and 4 cores, I can execute some number of transactions. As I scale up my architecture by introducing more processes and also more CPUs, I can get a relatively linear scalability. But this scalability becomes non-linear and quickly drops maybe to some steady state if your number of processes per core on average is way more than 1 per core. And there can even be a situation where you have so many processes per core that doesn't scale at all. And if you start adding more processes with more cores, the scalability actually decreases and your performance goes down. So those are the implications of the Oracle process-based architecture, or any process-based architecture. Now let's spend a few minutes talking about user response time, throughput, and database time. So user response time, there are 2 important things to user response time. Of course, how long does it take for a certain use case to run before the user has a result of the execution of that use case? And the shorter that it takes, the better it is, of course. But you also want user response time to be consistent. Consistency of response time is equally important. The variance in response time is what's going to cause your users to start disliking the application. Let's talk a little bit more about that. So here I have two graphs depicting on the x-axis here, the response time that a certain use case takes, and on the y-axis, how many times that response time was actually experienced by an end user. So the red curve has a single spike, saying that the majority of all the response times were what? Between 1.5 and 3.5 seconds with an average of 2.5 seconds. Yeah, there are very few response times taking a lot more and very few taking a lot less. Now the blue multi-hump indicates we have variance going on in response times. And we also have a long tail. So we have experiences taking 7 seconds up to nearly 8 seconds. And you want the red curve. You do not want the blue curve. And I'll come back in a few slides on how to achieve within your architecture, how to increase the chances of you getting the red curve and not the blue curve. But let's first talk about throughput. Now, throughput is the number of units of work processed within a period of time. So how many of these use cases I can get serviced by my database server for a certain time period. It's something different than response time, obviously. But as the system gets busier, your throughput will increase, very likely. Hopefully in a linear way, if your number of processes per core is close to 1, which is good. But the response time for each individual unit will also increase. That had to do with the first graph that I was talking about. Because your throughput increases, your system is busier, so your CPU busy rate is higher, the chances of getting higher elapsed times, of course, your response time of a single execution will increase. So that means that if you've witnessed, let's say, a throughput of X transactions per second when your database server was 40% busy, that does not necessarily mean that when you drive your database server up to 80%, your throughput will be 2x. Very likely it will be less than 2x. The third concept, real short, database time versus response time. So here I'm showing you a use case of an end user behind an application that issues an application request, and the application request goes to the application server and it needs to do 2 database calls. So it goes to the database, back to the application, issues a second database call, and then the result is sent back to the end user. So the response time is broken down across all these different components. The total user response time is the time spent on the network, the time spent in the application server, the time spent on the network between these two, and the time spent on the database server. Yeah, so a bit of gray, blue, red, gray, etc. So database time is just these 2 bits. Very often a very small component of the total response time that the end user experiences. Now, there's one point that I want to make also in this slide, and that is developers, when they look at the performance of the database, the developer, they will typically include this network time in what they call, it takes so and so many milliseconds for a database call to complete. Because from a developer's perspective, the database call starts here and it ends here. Whereas from the database perspective, it starts here and it ends here. Yeah? So the developer will typically add the network here to database time, or actually to how long it takes for a database call to complete, but it's not correct, of course. The other thing that I want to make here is we're now seeing customers move to the cloud, and sometimes they only move one of these to the cloud and the other one remains on premises. Imagine what's going to happen with this bit if you only move the application server to the cloud and you leave your database server on premises. Yeah, so this would be from going from sub-millisecond if these two are in the same on-premises database data center. And once this goes to the Frankfurt data center in our cloud, this suddenly becomes what, 3, 4, 5, maybe 6 milliseconds. Yeah? That has a huge impact on the performance of the application, because every database call would be increased by, let's say, 5 milliseconds additional here, 5 milliseconds additional here. Yeah, so your application server throughput will go down the drain if you only move one of these to the cloud and not both at the same time. So those were the 3 concepts that I also wanted to talk about: response time, throughput, database time. Response time, a single use case; throughput, how many use cases per second can I get through my system? And what's the database time component? Actually, only the red bits of those. 3 different things. Now, I wanted to come back to this graph. How can I ensure the red curve and not the blue curve for the end user experience? Because there's a core principle at play in this area also. Here's a different use case. And this time I'm calling the database 1, 2, 3, 4, 5 times. Yeah. So I have a breakdown like this, and I could tabularize it like this. I'm spending a little bit of time in the HTTP server, some time in the JVM, 6 times, some time in the foreground, 5 times for those 5 queries. The network outbound, I'm hitting only 2 times, and the network within the data center, I'm hitting 10 times. Those are these 10 little red lines here. Each time I hit the component, it has on average a certain duration. So I can sum up all those durations by multiplying the call count with the duration, and I get a total end user response time for my use case. Now, the way I'm showing this has a reason, because you get an idea that this is all linearly dependent on each other. And by that, I mean, let's say I have a use case that calls a certain component 20 times, which takes 2 seconds inside that component. The way this end user response time is built up makes you think that, let's say, if I re-implement that use case and it requires now 40 calls in that certain component, that you have a linear relationship. Yeah, because let's say if this if I go from 5 database calls to 10 database calls, and on average they have a certain duration, this 5 becomes a multiplier of 10. So it's a linear relationship, is what you think, but that's not the case. The actual relationship for each of these components is, the more you call them for a certain use case in your application, the more likely your use case will be hit by queuing in that component. Yeah. So the higher the call count, the more greater the chance is that you will spend some time queuing, which you did not well in the prior call. But it's not just that this now starts deviating and going up, taking more time on average. the variance also increases. Yeah. So in order to get the red single spike response time behavior, you want to minimize the call counts across components, across processes, because these are all separate processes. The JVM, the HTTP server, the foreground, and of course the network is also a component that you use and might spend some time queuing before your packet actually gets transmitted on the network. So the smaller the call count, the less likely you will be experiencing this variance, and therefore you get those single spike response times. So Oracle is a process-based architecture. To perform efficiently, you want to get on the CPU as fast as possible. You want to stay clear of those 100% busy times, also on your application server. It's better to call the database with more work in a call than to call it multiple times with little work. That's to do with the principle that processes shouldn't go to sleep voluntarily a lot. And you should use an architecture that requires a small number of processes. I'll have some more to say about this also in a minute. Yeah? And consistent response times require minimization of call counts across components. So if we see these kinds of things in AWR reports, we get an AWR report and we immediately see, okay, 23,000 calls per second, or maybe even 50,000 user calls into the database, which you can also see in the load profile. I personally like to look at this one first. And we see that every call is a very quick call, SQL engine requirement-wise, because they all execute a single row, which you can see in the SQL ordered by executions. So you're not wanting to stay on CPU long. And you have a 20-core server, and you have a factor 100x in terms of number of processes. So every core has 100 processes. So the OS scheduler does what it does best, descheduling processes all the time, making them experience involuntary sleeps. Here I have a situation where I almost have 150 processes per core on average. If we see these, we know that despite lots of CPU being burned, not much work is getting done, because the majority of the CPU time is spent on per call overheads. If we also see high busy rates, again, the response times probably aren't consistent. So one final topic. So I've talked about the core principles, core performance principles that you should be aware of if you're using a process-based architecture, which is what Oracle is. So what happened the last 2 decades with application development? Because it's my statement that it fundamentally moved away from these core principles. We stopped using the database as a processing engine, which is actually adhering to these principles. Let me explain that. So on a high level, an OLTP application can be viewed of, let's say, 3 major levels, 3 major layers. We have the interfaces, we have the business logic, the big chunk, the core of our application. And of course, we have the tables, the data store. And there are 2 fundamentally different architectures to build these applications. You can have all the business logic outside the database, inside Java, using layered software architectures, using frameworks, persistency frameworks, etc., inside a JVM, which have all these SQL generated and issued to the database. I sometimes refer to this as the no-pill SQL approach also. Or you can embrace all the business logic and have it run inside the DBMS, where you make heavy use of both SQL and peel SQL. Now, these 2 different architectures fundamentally deal also differently with the core principles that I talked about. Let's give you an example here. So here I have a use case where I'm depicting it in peel SQL code, but think of this being Java code. So we have some Java code and it selects a single row from orders to retrieve the limit. It then inspects the limit. And if it's more than 2000, it says, okay, well, I consider this a high risk order. I want to go across all the order lines. So it submits a second SQL statement and starts fetching these row by row, all the order lines of that order. Then per order line, we look whether it's open. And if the discount is more than 10, I'm going to decrease it by 10 because I consider this a high risk order. I want to decrease it by 10. Otherwise, I set it all the way down to 0. Once I've done that in my program variable, I'll bind that program variable again to an update statement to update the actual row in the database. Yeah? So we have bits of business logic going on outside the database, and then single row SQL statements. Now, if you look at this particular use case, it could actually be done in one single update statement. And that's what I mean by using SmartDB or using the database as a processing engine. I could update the order lines, set the discount, decrease it by 10, ensuring it doesn't become negative, of open orders who I consider, of open order lines who have a parent order that I consider to be of high risk. That's a single update statement. Yeah? We hardly see these kinds of statements anymore in modern applications. Yeah? It references more than one table, affects more than one row. Why don't we see this? Because all the SQL nowadays is generated for the developers. All these frameworks that they use inside the Java layer, they generate row by row SQL statements. They can't deal with these complex business logic containing SQL statements. Whereas in the situation where you have your business logic outside the database, you are calling the database multiple times. Yeah? I'm going to retrieve the order. I'm going to retrieve the order line, update the order line, retrieve the next order line, update the order line, retrieve, etc. Whereas here I send a single update statement. Yeah? So immediately you see that these new architectures, they call the database orders of magnitude more than a different architecture that's also there and available to you would require to call the database. So we have high call counts between processes. Fundamentally different architectures. All business logic outside the database implemented in these layered software architectures, whereas SmartDB using PL/SQL and the database engine as a process engine, basically only the user interface sits outside the database. Oracle Apex Application Express is the prime example here. Many small calls to the database leading to a high rate of voluntary sleeps. Only one user experience is one database call, reducing voluntary sleeps. Noticeable per call overhead as the call is a fast executing SQL statement. Here, of course, you also have the call overhead, but my call now does a substantial more amount of work. It wants to stay on CPU much longer, and the call overhead is, in terms of the work being done, not noticeable anymore. Of course, the number of times we hit this overhead has reduced an order of magnitude also. Now, I also make the statement here that these new software architectures require a large number of foreground processes. You probably have seen connection pools in your applications into the hundreds or maybe thousands of connections going into the database. Whereas these architectures require a very small amount of foreground processes. Now, I'm not going to explain that in this talk. There's too little time for that, but there's a YouTube movie on just this topic also. Again, if you go to YouTube, I did an Ask Tom session. You just search Ask Tom connection pool. The top one will give you a full hour talk on explaining why this approach requires a large number of foreground processes and this approach does not require a large number of foreground processes. It basically has to do with the network time between the application server and the database server. That network time basically implies that the foreground process will not be busy during that time. So your architecture is not capable of loading foreground processes. It implies a certain percentage of idle time per process. And that then implies that you need more processes to get the database busy doing work. Yeah, so I talked about all this. Every SQL statement requires those 4 before it arrives at the SQL engine. So you have those fixed CPU overheads, and it could be a 2x knock-on. I think I also have a second AWR snapshot on the next slide. Again, I said this is not just on the database server where you have all these context switches and fixed overheads going on. It's also happening on your application server. Now, who's using microservices? Very likely some of you have applications that have been built using this, what used to be very popular microservices architecture. So here I have this use case again that calls the database 5 times. Let's say I'm going to add 2 microservices to it. There's a microservice here at the start, which calls out to a different JVM to check the balance, saying that this is a bank transaction. And it's a synchronous, or not, maybe not even, needn't be synchronous. Let's say it's synchronous. So I go over there in a different application server to check the balance. I do my work, I do my transaction, and at the end, I'm also gonna call a microservice that audits my transaction. So stores audit information in a different audit database. Yeah. So if you have applications like this, not only do you have more components and risk a more variability in the end user experience times, of course, this whole architecture is rife with per call overheads. Yeah, you can have dozens of application servers burning lots of CPU, but not doing much useful work. Almost half of those CPU are per call overheads. So what I wanted to show you is this little snapshot here from an AWR report. This was an actual investigation that we did a few years ago, where we saw a database server being busy 50%. So that's not bad. 50% is a busy rate where you can get fairly quickly scheduled onto the database. But notice the number of sys CPU. You want this to be like a couple of percentage points, but here it's almost 1/3 of all the CPU being used. So the fact that you have a high percent sys already is an indicator, a red flag, probably indicating that you are calling the database a lot of times per second using small calls, 27,000 in this time. In this particular case, we also investigated the CPU used by the foreground process, and it turned out that half of these 32% was Oracle code entry and exit point, because the SQL statements were really small and really fast executing. Yeah, so I'm burning 50% of the CPU, but only 1/3 of that 50% is doing useful application work. The rest is all overhead. You're not using the database as it was designed to be used. That's the major issue here. If you want to reduce your computing resources, you should consider the other architecture. You should consider implementing much more logic inside smart set-based SQL and PL SQL using as the embedded programming language from which you submit all your SQL statements. And now my statement here is, if you have an application that's built like this, and you move it over to an architecture like this, I'm going to make a statement here, a bold statement. Your database will be less busy. It will be less busy. We've witnessed this. Why? Because the massive reduction in call counts gives you a great reduction in CPU used on your database server, both sys CPU and user CPU. The gains that you get from reducing the call counts by moving to the different architecture outweigh the business logic that you bring into the database. So the cycles that you free up easily enable you to implement business logic in the database, and you still have headroom. That's why I say your database will become less busy. I think seeing this is believing it. You might do simple tests yourself to figure this out yourself. So in summary, the majority of the current applications have large computing resources footprints because they were built using layered software architectures where all business logic execute on application servers, giving rise to high call counts per second. Yeah? And they thereby violate all database core performance principles. If you want to reduce your computing resources footprint, don't bring data to code. Bring code to data. Yeah? Don't bring data to business logic in the JVM. Bring business logic from the JVM into the database using Smart SQL and PL SQL. You need to focus on minimizing chattiness, process context switches, call counts, etc. You'll not only find that your database server becomes less busy, your application servers as well. The footprint over there will reduce greatly, and your user experiences will become more consistent. And with that, I would like to finish this talk today. If you have any questions, you can email me. You can also find me on Twitter. And Rodrigo, I don't know if there's questions. I think we have 5 minutes for questions. I'm not hearing anything.
Yes, Rodrigo is checking the questions. At the chat at my side, I have questions.
Okay. I was trying to find the button to unmute myself. So I don't see any questions. We have 5 minutes for questions. So people, you can do now the questions to Toon. And also, as he said, you can after send some by email if you wish. Okay, Tom, we have a question asking you to share the name of the book.
The name of the book.
Okay, let
me go here. Applied Mathematics for Database. So this is a book. Let me just make one comment about it, which focuses on this bit, database design. So beware. This is basically explaining the mathematics behind the relational model of data as it was invented by Ted Cott and evangelized by Chris Date during the 80s and 90s. So it gives you a mathematical background on how to design databases in a correct manner, adhering to the relational database theory.
We have one more question. How to convince the current developers focused on microservices to meet the best practices?
Yeah, it's extremely difficult to convince developers. My experience has been they can't be convinced. They know they are right. The only thing that I can show them and the only material that I confront them with is actual data. Show them AWR reports where you can see the evidence of the overhead. Show them, well, but that goes a little bit further. Show them profiling data of the various processes. Show them how much time their JVM is spending on useless work, sending JDBC statements out and receiving statements back. Yeah, because these developers, they will make claims. Well, I have 4 application servers, all 8 cores, and they are busy 80% of the time. No way this can run in the database. Well, the statement here is those application servers and all the CPU they burn, well, right off the top of the head, more than 50% is useless work. Then, let me just show you one more time, this flame graph of the JVM. Then I'll stop. So this is overhead. This is just JVM housekeeping. This is where the program was actually running. If you zoom in on here, you'll see the majority of the time is spent in JDBC layers. The majority is just going down and up JDBC layers. This is going in and out of the process. This is going up and down JDBC layers. If they're using frameworks, you'll see much more overhead here. And all that overhead disappears if you start using set-based SQL and PL SQL in a smart way inside the database. My statement here is if you're spending 100 seconds here, I can replace that by a single second inside the database by using the database the way it was designed to be. Yeah.
Perfect.
And with that, let's move on to the next speaker, right, Rodrigo?
Yeah.
Yes.
Okay.
Thank you so much, Tom, for your presentation, and thank you, the attendees, to being with us today. And we will go to the next speaker. Will be Pete. Pete. So, Fernando, it's on you.
Yes.